Hello guys. Yes, how are you? Haven't seen you for a while. You won't see me for another 2 weeks. But however, as you may know that I'm still in Hong Kong. So what I would like to do is to give you guys a few videos for the first 2 to 2.5 weeks. For year 12, definitely is not an ideal case. But this is, I think, is the best I can do. It may be easier than just grab someone coming in and start the unit with you. So let's see, have a look what we do. We don't really have a big class, so I'm very available. So if you're going to send me the email about whatever problem that you encounter with these 2 weeks, I'm very happy to help you out. All you need to do is to keep update me your progress. So make sure that you know my email and make sure that you have your Dropbox ready. So if you were here last year in the orientation week, we should have the Dropbox ready in your computer. So let's have a look what we do this term and what we do basically unit 3 for this. So if you still have any problem, just make sure copy this down. This is my email address. You should have it. alia.vic.edu.au. Yeah, make sure every time when you hand in your work, when you try to ask me questions, send everything to this email. I try my best when I have the internet connection, I will try to do it. I do plan to have a video conference classes today with you guys, but it's very difficult for me to find a quiet place in the morning in Hong Kong with the good internet connections. So I have to change the plan and make a video for you guys. Hope everything will work. Yes, don't waste our time. I'll try to start off the very first class of the year. First of all, make sure that you do have your Dropbox. You know that I love it. Last year I will have every single thing that we do in the Dropbox. So in the Dropbox account, what do you see basically for maybe the first time? My computer is a little bit slow. In the Dropbox, you'll see this particular one is 2018 Year 12 Chemistry. So when I click into it, this is the file that I'm going to share with you. Definitely you have the 2017 version textbook. That is the major one that you're going to use. All the chapters in there, chapter 1, 2, all the way to 12, and I'll give you the page numbers that I refer to based on this textbook. But if you think that the first textbook is not good enough, I do have all the other textbooks that I have over the years. 4 different textbooks like Chem, Dimensions, Heinemann, Nelson's, and Study On. They're all very good chemistry book. Good at certain topics. So sometimes you may find me referring to one particular textbook, not the others. Just pick the good one for you. Then you will see that under orientations there would be exercise in it. Remember, I gave you this exercise last year. You should start doing that over the holiday, but if you haven't started, it's okay. I'd like you to give it a go as well while we're doing this video teaching. And week 1, so this is basically the week 1. When you click on week 1, you will find that there's a Year 12 workbook. This particular workbook would be the one that you need to finish before I come back. You have all the details that I need you to know from a textbook. For year 12, we don't have time to get lazy. So please make sure this particular workbook need to be filled in while we're doing the notebook or while we're doing this teaching. So let's start our course. Now, let's cross this one out. And I believe that you have copied my email address. I'll clean this one up. Now, let's start Unit 3. So Unit 3, as you may notice that we have one exam for this year. It's easy with Unit 3 and Unit 4 combined with a 2.5 hours exam at the end of the year. It is different from many, like 5 to 6 years ago. That would be separate exam. And last year we started a new syllabus. So then everything changed a little bit, but I'm not really familiar with this change. So I'll try my best to put everything together for my understanding. That means you will find the topics I put together may not be the same order that you find in the textbook, but I think that's the best way. I like to remember it that way. So do you, because you're my students. I can't change myself. So just stuck with it. Let's see. Basically, the Unit 3 in the new syllabus started last year is all about fuel. The main topics about that is about fuel, about energies, about where do you get those energy from. In order to get that, because I have my cheat sheet here right next to me, so you will find me looking at the cheat sheet sometimes. So this particular fuel, first that you will find that fossil fuels would be one of the major ones that we use in our society nowadays. What fossil fuels related to? It related to all the dead living things. It could be all different types of, like, would be a marine creature, all the way to all the grass and the wood, and all the vertebrate, invertebrate animals. So those come from previous life. All the fossil fuels has been it's understand. It's been buried underground for many years. It created a big problem because it's supposed to be buried, and all the carbon should be trapped under the underground. But when we start using those fossil fuels, we release those carbon into the air, and that is one of the major source of carbon that make greenhouse gases. There will be a lot of greenhouse gases in the atmosphere, but one of the major ones is carbon dioxide. Another one is methane, CH4. The first field that we study would be fossil fuels, and then there would be some other kind of more clean energies that we would like to introduce. Solar energies, we all know that come from the sun, and there would be something, I classify this basically a clean energies, because in terms of the carbon footprint for nuclear energies, this may be one of the lowest in terms of the carbon footprint. However, the waste coming out from the nuclear plant would be really difficult to deal with, and high radioactive materials in there. The other two that you may not kind of like familiar with, one of them is called hydrogens. If you come to my year science class in the year lower form, year 10, year 9, I always talk about hydrogen, because hydrogen could be a good source of clean energies, and there's lots of research doing how we can utilize those hydrogens in our life. Hydrogen is one thing as a fuel, and more and more for the last 20 or 30 years, there's a new concept called biofuel. And this biofuel has fuel. Basically, it's fuel very similar with fossil fuels, but it's coming from life. This life is not previous one. It's basically is the current life. May not be directly coming from plant or the life that we not directly. It could be indirect way. For example, there's some ethanol you can make out of life after fermentation process, and we have some other thing called biogas. So if you look, if you're standing right next to the dumping site, you always see there's a tube there keep burning the gas out. Those tube is important because when the food or when the plastic or organic matters get decomposed, it will release lots of burning gas, including methane and other small hydrocarbon gases. And those gases is a good fuel. So lots of dumping sites trying their best to trap or gather those gases and recycle them. The last one is interesting to see. We call them biodiesel. Biodiesel is not a diesel fossil fuel, but has a very similar chemical properties and burning capacity with it. So that's why we call them biofuels. But there's nothing related to fossil fuels at all. It can made by living things. Mainly, nowadays we try to use the waste oil to make those biodiesels. Yes, by looking at those 1, 2, 3, 4, 5 different areas of fuel, and we would look into there a little bit more details later on. Most of the time when we deal with fuel, there's one concept that we cannot escape, which is this big term: energies. What is energies? So energies, you cannot destroy it. No one can tell you where this is from. It's there from day times 0. It would be there at the end. It's always there, and these energies can be at different forms. So there's lots of common form of energies that we encounter. So you can see things because our eyes can detect the light energies. It's a form of energies, and we're also able to say potential energies. For potential energies, it could be a chemical or physical. What do I say? Physical or chemical? Chemical potential energies means that a complex molecules can hold up lots of energy in there, and is ready to break it down and release some of the energy stored in it. It's a potential energies. Or you can say a physical potential energies. You put a rock at the top of the mountains. Once you push it, it cool down itself. You have plenty of potential energies in there. What else can we do? One of the things that we do a lot is heat. Heat is the type of energies. And one more thing that we can't live without it nowadays is electricity. So electricity is a form of energies, heat and the light and the chemical potential energies. So those energies, you can say it changed from one form into the other form, and they would never end. It's always from one transform into the others. And you, as I said before, you cannot destroy energies. So in the exchange process, to do field, first of all, field provide form of energies, and at the end we're going to consume it. But from the field, from the starting as a field, and this has the potential energies in there. Most of the fields that we talk about has lots of chemical potential energies in it. It's a complex chemical molecules. Then when you start break it down, we consume those energies that release. But how much energies do we actually consume at the end? And how much energy is actually being lost throughout the process? And we have a particular term to describe this. We call them field efficiency. So field efficiency is quite easy to calculate. So basically, if you have 100 kilojoules in a field that you expected, but at the end that we are able to consume about 50 kilojoules at the end, and that means you have lost 50% over the process, over the transformation process. So definitely when you try to think about technologies and what we do in technologies, all the engineer people we do, they try their best to minimize those lost throughout the process, and that means they increase those field efficiencies. And as a chemist, we try to develop a product or try to make some products that we want at the end with the least of the energies input. That's always our goal, and that should be put behind our mind when we design anything. So when you try to look at field, there's a big word that you may not encounter before. We call them thermodynamic chemistry. In terms of thermodynamic chemistry, thermal means temperature, dynamic means lots of things keep moving, and in this particular topics, we think about there's a reaction going before and after, and before they interact, and then after they interact. To show those chemical interact, equation is very useful. And let's say a very simple example of burning fuels. We have hydrogen as one field, and it combusts with the oxygen, and once those two react, all the reaction and all the things, the atoms start rearranging and form water at the end. And we need to pay attention to it. This equation here is not balanced. So in order to balance these equations, we like to put a 2 in front of the hydrogens and then put a 2 in front of the water. And all of them just assume that they would be gases. If you try to think about this is a combustion process, burning fuel reactions. In terms of thermodynamic chemistry, we can't just stay there saying, looking at the chemicals. There's only 2 chemicals at the 1, 2, 3 chemicals before the reaction and 2 molecules after the reaction. That's not the major purpose about thermodynamic chemistry. In terms of thermodynamic chemistry, we need to look at the energy change. And the energy change can have another term called delta H, or heat change, or some people just say called enthalpy. And they all refer to the same thing, is the energy difference before the reactions and after, before and after. Just try to find out the differences. So if you're talking about this, how can I put the information into the equations after I have like balanced it? We have a general practice. Just write down the shortened form of energy change, which is called delta H, equals to whatever number that we measure. Then energies is measured in kilojoules, and because is in molarity, because it's much easier to measure everything in mole, so we call them per mole. So in terms of this particular unit, we may say that per mole here doesn't mean that per mole of every single chemical. So does it mean that we have 1 mole of hydrogen, 1 mole of oxygen, and make 1 mole of water? They are not. Mole there just means that we're using mole to measure. But in particular, trying to look at the equations, the coefficients play very important roles. The 2 in front of the hydrogen means that if you put 2 mole of hydrogens react with 1 mole of oxygen gas, you will produce 2 mole of water. It means, let's say this particular reaction there, I say is X kilojoules in there. If you burn 2 mole of hydrogens, it released X mole of energies. Not just 1 mole of hydrogens. Mole is used to give a unit for every single molecules. Okay, hopefully you get a little bit get into a little bit more details. You will find that it will be easier to grab about those concepts. Okay, as I say, there will be measurements about heat change, and the major unit that we use is kilojoules. Not KO, kilojoules, KJ. Sometimes when you have such a small amount of energies, we may try to do it just as joule, right? And sometimes when you try to say, there's a huge reaction taking place, we may say that we have a megajoules. Megajoules basically means 1,000 kilojoules. So if we say what is 1 megajoules? 1 megajoules would equals to 1,000 kilojoules as well, equals to 1,000,000 joule. Right? So it's simple chemical conversion between each other. Then if you try to look at a reaction just we have before, 2 hydrogen gas with 1 oxygen to form 2 water. This particular process, we would like to describe the energy change before and after. A graph can be used to describe those energy change. Those graphs, we give them a name called energy profile. In energy profile has a x and y axis. For the x axis down there, probably you can imagine it's like a time, but it only has 2 period of time. It just you want to focus on the beginning and the end, and that's it. So talking about the differences of the start and the end. Before the reactions, it's right here. Before the reactions, and after the reactions. Before, then after. And what would be the y-axis in here? The y-axis is the energy content. So the lower energy content and then the higher energy content. Or you can start with from the high energy content to low energy content. In terms of this particular reaction that we have, hydrogen gas and oxygen gas and water. Water is one of the major molecules that you can find and is really stable. And when the molecule is stable, it generally contains less potential energies. Hydrogen and oxygen, both of them contain relatively higher energy content. Then when they react, it releases those energies and turn into water. And we call this energy profile. By looking at the energy profile, it's clearly the start of the reactions is really high compared with the end of the reactions. If you're looking at a reaction as a what we call enclosed system. So let's say we put a hydrogen gas and oxygen gas in a bag, and in this sealed bag, then you try to make a spark, then all the reaction take place, it turns into water. So this bag here is as an enclosed area because inside the sealed bag. And this enclosed sealed bag contains hydrogen, oxygen, and water. In chemistry, we call them a system. And this system have left-hand side and right-hand side. When the system interacts with the surrounding area, so a plastic bag with all the surrounding area, which is like, let's say, is on the bench. Then, when it burns, it has a lot of heat. And where does the heat goes? And the heat goes into the surrounding area. If I'm in the science room, I would basically do this with you, mixing two chemicals in a plastic bag, and once they release the heat, you can really touch the outside of the bag and start heating up. And the temperature, because the energy is releasing to the surrounding, then the energy is kind of like burst out. When it bursts out, we can easily sense it, and the surrounding temperature will increase. You will have an increase of temperature when two very reactive chemicals react. It has a higher chemical potential energies, and when they react with each other, they go down to the lower chemical potential energies. And the energy released to the surrounding, and the whole thing, we give them a very easy word to remember. We call them XO. XO means release. Thermic means temperature. Reactions. We have exothermic reactions in there. And in the exothermic reactions, the chemical contents of the product at the end of the reactions compare with the energy content before. So here is the before one, that's the after one. And those energy contents, I like to use the red one there, so energy of the product, PUCT. And then you have another colors to represent this is energies of the reactants. Compare between them, the energy, the reactance is bigger, way bigger than energy product. And what would be the delta H? By definitions, the energy change is equals to the energy content of the product. Take away the energy content of the reactants. So for the product and reactants, as the product is smaller than the reactants, and we will find that we have the negative number at the end. And negative number doesn't mean that we destroy the chemistry, destroy the energies. The negative sign refers the flow of the heat. The flow of the heat is coming inside to the surrounding, and we call them negative. So what is another situation? Another situation would be saying that we have the energy profiles here. We start with a very low chemicals, and then we end up with a high chemical process. One of the major or very common example that I use would be photosynthesis. You need to remember, you need to memorize the reactions of photosynthesis. It begins with sugar. It begins with carbon dioxide. What I'm doing, we begin with carbon dioxide, and it integrates the carbon dioxide into the water. Then it forms glucose. And everything with 6 carbon, 6 water would make 1 glucose, and a byproduct is O2. You have 6 of them as well. So this one is easy to remember. A lot of 6 CO2, 6 H2O, then produce 6 O2, then make 1 C6H12O6. And this reaction, you can see the chemical C6H12O6 and O2, both of them we classify as a relatively higher chemical potential energies compound. Is right up here. Really, I'll say high potentials. They're very good high potential energies, contained lots of energy inside. Then for the carbon dioxide and water, they're very stable and calm molecules. They don't really have a lot of energy in there. What you do, you try to push those all the way up from the lower energy level to from the low energy content, push that up into high energy content. According to the formula, the energies of the product take away the energies of the reactants is the way that we calculate the heat change. And what does that mean for the heat change here? For the heat change here, we can see that would be a positive number. As, oops, something's funny. Give me a second. Yes, fill the gap here. The positive number. That's better. So the product is above here, and the reactants is down there, and the product P is way bigger than the reactants. in these situations, the heat is no longer going out. Instead of it, your system is right here, running as carbon dioxide and water, and then glucose, and then oxygen. And we've got the surrounding. Surrounding here is responsible for giving the energies to the reactant, then push it all the way up to the product. Therefore, the heat would go into the system. If you try to steal some heat from the surrounding and land it to the system, and what happened to the surrounding? You will find that the surrounding will have a decrease of temperature. So you will say from 50 degrees down to 20 degrees, or no matter what, your temperature would drop. And a big terms to describe this type of energies, we call them endo energy. Go into the system, thermic reactions. Endothermic reactions. Right? Just to finish up today, I know the very first class, I'm not going to, you guys going to chem next week, I'm not going to give you a lot of hard work. For the next thing is basically trying to look at the energy transformations. So let's say we have a car running on the road. We have a few energy transformations that happening in the car. First, the car is not moving, and you've got all the chemical energies in your fuel. Make sense? Then your chemical energies need to combust in your combustion engine, and you turn it into heat energies. You release all the heat, and the heat expand the air, and then all the heat make the engine move and become motions. And the motions would be called kinetic energies. Right? As the car's moving, from the kinetic energies, you think the wheel is moving, basically try to overcome the frictions, as well as the tires get heat up. And the last transformation would be it turning into heat again. And then another type of kinetic energies. So kinetic turn into kinetic, we don't have to mention it. So when you try to look at the basic transformations in the car, you have a chemical energies turn into heat, and then kinetic, and then go back to heat. So all the things, energies, we haven't changed a bit. We haven't destroyed any energy, we haven't created any energies, but we transform from one form into the others. And you will have a few works to do this week. I'd like you to focus on your workbook. In your workbook, I think it's just page 1 and page 2. Is a very, very brief, simple questions about energy transformations. I need you to have a look at them. The file would be like this. Give me a second to open it. So your work would be you should have your workbook now, but I asked the office to hand it out. So if you don't have your workbook, you need to go to the office and ask for one. So year 12, 2000, then week 1 there, you will find a Year 12 workbook. And inside the Year 12 workbook, yeah, the computer is working hard. I'm trying to upload the other videos, recording this video, and try to open all the words. It's overloading it. It's so slow now. Give it a second. Open, please. Yes, here you are. So you are going to look at part A this week. So you have a few questions. The first one is a fire. It started a campfireplace by striking a match and lighting a piece of crumbled newspaper under a pile of dry twigs. And you need to explain the transformation process in between them. And what does that mean for the 30% energy efficiency for question 2? Describe the energy transformation and blah and blah. Question 5, energy transformations. And question 6, you have gigawatt. What does gigawatt means? You also try to look at the 3 examples of biofuels. Try to give me some ideas. Advantage, disadvantage of ethanol and petrol. Right? And sometimes you would also like to talk about assuming the carbon dioxide, the last one, explain why production of carbon dioxide may lead to environmental problems. So hopefully you will have a look at part A yourself and make sure that you read chapter 1. Okay, chapter 1 in your textbook. Yeah. It may be it makes to the end of the video, and I just put the end here to do it. So overall, we will have a total of 6 videos. So 6 videos, this one down, and you have another 5 to go. Make sure you check your Dropbox probably every day, and you will need to watch all the videos and do your workbook. And this workbook, the first one, I don't need you to do some guided questions. For the rest of it, I will have a guided question for you. You need to finish them as well on top of the workbook. Yeah, hopefully it works, and hopefully you have a good break and also have a good time next week in the camp. Okay, see you. Bye bye. Thank you.